Helicopters. These gravity-defying machines can get you from point A to point B, flying forward, backward, sideways, or stay perfectly still in the air. They can take off and land vertically from every surface imaginable, all through the power of aerodynamics, and maybe a little black magic too. Now, if you're anything like me, just the thought of trying to understand the complexities of a helicopter is extremely intimidating. But I am going to show you in this video that anyone in just 15 minutes can understand the basic principles and physics behind how they work, without wanting to bang your head against a textbook or a 1997 PowerPoint. Hopefully. Now, there are 4 basic forces acting on every aircraft during flight: gravity, lift, thrust, and drag. So in this video, we'll be covering how helicopters generate lift even when they're staying still, and how they can generate thrust in 360 degrees. And what are the different control surfaces that pilots use to change these forces to actually fly the helicopter? And lastly, what happens when helicopters lose their engines? All coming up in this not-so-crash course to how helicopters work. Lift is the force that opposes gravity, enabling the aircraft to fly upwards. On helicopters, lift is created by the main rotors on top of the body of the aircraft. These rotors consist of multiple blades, which create lift in the same way wings do on an airplane. Now, I covered how wings generate lift in my How Airplanes Work video, but here's a quick summary. Lift is determined by 2 main factors: the shape of the wing, also called an airfoil, and the angle that it makes with the oncoming airstream, called its angle of attack. Now, you notice that many planes will have airfoils with a cross-section that looks like this, with a higher curvature on top and a straighter surface on the bottom, and that is to turn air towards the ground. The oncoming airstream will be split into 2 paths, one above and below the wing. The air molecules above the wing will stick to the surface, following its curvature downwards. This is due to what is called the Coanda effect, and is the reason why if we pour out of a pitcher slowly, the water will run down the side as opposed to pouring straight down. So as the upper air molecules follow the downward curvature of the wing, 2 things happen. First, the air is turned in a downwards direction. Now, we know from Newton's 3rd law that for every action, there is an equal and opposite reaction. What this means in this case is that since the wing exerts a force on the airflow directing it downwards, then by Newton's 3rd law, the air must also exert a force on the wing, pushing it upwards, creating lift. Now, at the same time, an area of lower pressure is also created above the wing, since there are now more space for the molecules to occupy, and hence the air below the wing wants to equalize this difference in pressure by pushing upwards, again creating lift. Now, you might be wondering, how would planes fly upside down? Or how would planes with flat wings fly? Well, the answer is the second factor affecting lift, the angle of attack. Now, by tilting the airfoil upwards slightly, the air beneath the wing now gets compressed into a smaller space, creating an area of even higher pressure and creating more lift. Now, at the same time, these air molecules are also forced downwards by the wing that is in their way, again creating more lift. So that is how wings on an airplane generate lift through the shape of the airfoil and their angle of attack. And the exact same thing is happening on a helicopter. Except as opposed to the entire plane moving through the air to create lift, each blade on the rotor moves continuously, just in a circular path. Now, of course, the more blades, the more lift, so let's add a few more. There. This is how helicopters generate lift, even when they're staying completely still. But there is an important difference between helicopter blades and airplane wings. Now, as we mentioned before, a wing with a higher curvature upper surface will turn the air downwards to create lift. This shape is called a cambered airfoil, but on most helicopters, the shape of the blades is non-cambered or symmetrical between the top and the bottom. Symmetric airfoils can't actually generate lift at 0 angle of attack, so they need to mostly rely on their pitch to generate lift. Now, the reason why we use symmetric blades on helicopters, even though they create less lift, is blade twisting. Now, as an asymmetrical airfoil changes its angle of attack, its center of gravity also changes. Now, on a plane, that's not really a problem. But on helicopters, if the center of gravity of a blade is too far ahead or too far behind its pivot points, this will cause the blade to start twisting. Now this adds unnecessary stresses to the blades, and hence most blades are symmetrical to avoid this, and rely mostly on their angle of attack for lift. But there's another problem. By Newton's third law, since the main rotor is spinning in one direction, this rotation exerts a force on the rest of the aircraft. That is, the body of the helicopter wants to spin in the other direction, and this turning force is called torque. Now obviously, it wouldn't be very fun or safe for every helicopter flight to be a spinning teacup ride, so we need to add a force to counteract and oppose this spin. Enter the tail rotor. Now the tail rotor works exactly in the same way as the main rotor, just placed on its side. Similar to how a propeller on a regular airplane works, it creates thrust in a sideways direction to keep the helicopter stable. Now the tail rotor is a very common solution to counteract torque, but there are many more. For example, there are also designs with two main rotors spinning in opposite directions. This is called a coaxial rotor. There are also fenestrons or fantails, which have tail rotors embedded in the tail. Also, there are tandem rotors, one on each side of the helicopter. So now you understand the basics of how helicopters work, but there's more. So you might be wondering, if more blades create more lift, why don't we just add more blades and create infinite lift? Well, not quite. First, the tip of each blade creates a wake turbulence behind it, since at the tips, it's easier for the high-pressure air molecules beneath the airfoil to simply escape from the side than to push upwards to create lift. This creates vortices behind the blade and affects the performance of the blade behind it if they are too close together. In addition to that, each blade adds additional weight, meaning it will require more lift as well. Also, more blades add to the complexity of the hub, increasing the risk of failure and also the cost to produce. This is why we see a lot of smaller helicopters with only 2 blades. Now there is another reason why helicopters can't just produce infinite lift, and that is wave drag. As the tips of each blade approach supersonic speeds, they form shock waves as pockets of supersonic air push on the surrounding air. These pockets create massive amounts of drag, called wave drag. This is the limiting factor on how fast blades can spin. And there are many more components to drag as well, namely parasitic drag, profile drag, and induced drag. Parasitic drag comes mainly from the physical frontal area of the aircraft as it displaces airflow away from the helicopter. This is similar to why we feel resistance when we move through water. The drag from the surface of the helicopter, called skin friction drag, also contributes to parasitic drag, although to a much smaller degree. Profile drag comes from the component of the airflow that doesn't stick to the surface of the wing. This includes the wake turbulence that we just discussed. Both parasitic and profile drag increases as airspeed increases, and hence they limit the efficiency of the helicopter at higher speeds. On the other hand, induced drag is the major drag factor at lower speeds. Induced drag comes from the generation of lift. Since the lift force is actually perpendicular to the blade's surface as opposed to pointing straight up, there is a component of this lift that points backwards, and that is induced drag. So as you increase the angle of attack, you're also producing more induced drag. And since higher angle of attack is required to generate lift at lower airspeeds, induced drag increases as you slow down. All put together, the total drag of the helicopter looks something like this. So those are the 3 main sources for drag: parasitic drag, profile drag, and induced drag. Unlike an airplane with propellers or an engine that produces thrust in one fixed direction, a helicopter actually uses its main rotors to create thrust in 360 degrees. This is done by actually changing the pitch of each blade at different positions on its rotation. For example, say we want to generate thrust to the right. Then when the blades are on the left side, they change to have a higher angle of attack than when they're on the right. This generates more lift on the left side of the aircraft and essentially causes the helicopter to roll, and hence the lift force becomes tilted to the right, creating a thrust component in that direction. And the helicopter moves to the right as a result. So you'll notice that as we produce thrust, we're also losing lift. This means that if a helicopter accelerates in one direction, it will actually descend. So we can see that a change in one force actually affects others as well, and this is the reason why flying helicopters is so challenging. Now there are 4 main controls in a helicopter: the collective pitch, the cyclic pitch, the anti-torque pedals, and the throttle. The collective pitch controls the pitch of all the blades at once, collectively. In other words, it controls how much lift is being generated by the main rotors and causing the helicopter to climb or descend vertically. The cyclic pitch is what enables main rotors to create thrust in different directions. This is by changing the pitch of each blade individually depending on their position. So the cyclic looks similar to a joystick on a regular airplane. The anti-torque pedals control the amount of thrust being generated by the tail rotor, so this enables the helicopter to change its heading left or right. And lastly, the throttle controls how much power the engine produces. It ensures that the blades are turning at a constant RPM even though drag forces acting on the blades change throughout flight. Now this sounds pretty simple, right? But remember, a change in each control requires changes in others too. And on top of that, these controls aren't actually changing the helicopter's position, they change its acceleration. Here's what I mean. Say you want to move a helicopter 1 meter to the right. You can't simply move the cyclic to the right and stop when you're done. You need to instead move the cyclic to start accelerating to the right. And once you reach the right airspeed, center the cyclic. Then as you approach where you want to be, you need to move the cyclic to the left to start decelerating. The further left you move the cyclic, the faster the deceleration. And as the aircraft comes to a stop, center the cyclic. But if you've overshot your position, you need to repeat the whole thing again. But we're not done. Through moving the cyclic, we also decided to trade some of our lift for sideways thrust. This means that our helicopter has descended in the process, so to stay at the same altitude, we need to use the collective at the same time to generate some more lift. But when the collective is raised, it creates an additional load on the blades that needs to be counteracted by increasing the throttle to maintain RPM. Oh, and during this entire process, you also need to use the anti-torque pedals to make sure your heading stays the same. And this is all just to move 1 meter from point A to point B. Easy, right? So as if flying perfectly functional helicopters isn't hard enough, what happens when they lose their engines? Now, contrary to popular belief, helicopters don't just drop out of the skies when they lose power. They can actually land safely using their remaining airspeed and altitude, similar to how planes can glide when they lose their engines. And on helicopters, this is called an autorotation. When a helicopter loses its engines, the pilot needs to lower the collective to reduce drag to keep the rotor spinning, which still creates a small amount of lift and thrust as the air is directed backward. Now, at the same time, the loss in potential energy from the aircraft losing altitude is converted into kinetic energy, keeping the blades spinning. And as the helicopter approaches the ground, the pilot needs to lift up the nose, called a flare. This is in order to reduce the forward speed and also increase the RPM of the rotors in preparation for the final step. The pilot can then trade the remaining RPM to increase the collective right before touching down to produce a bit of lift to cushion the landing. And of course, in the process of creating this lift, drag will slow the RPM of the rotors to 0. But hopefully by that point, you're already on the ground. So that is the basic sequence of an autorotation landing, and throughout this entire process, different parts of the blade are actually doing different things. There are 3 main regions. Around 25% of the blade closest to the hub is the stall region. The airflow around this area isn't contributing much. From 25% to 70% of the blade is called the driving region, which interacts with the upwards airflow to keep itself spinning. The outermost 30% is called the driven region, where lift is being produced as a result of being carried by the driving region. So in other words, you can think of how blades work during an auto-rotation as how work is being divided in a group assignment. So now you understand the basics of how helicopters work, and also got a glimpse into the incredible skill that it takes to fly these machines. Now at the same time, that is just the tip of the iceberg. There are still so many more topics that I didn't get to cover in this video today, but I hope that by watching, I've sparked a little bit of curiosity for these incredible machines that you'll go learn more. Now, as I mentioned before, I am still a complete beginner in all of this, and there's still so much learning left for me to do. So as you conduct your own research, feel free to come back and let me know what I missed in this video. Now, if this is the first video you've seen on my channel, welcome. I typically do a series called Airplane Anatomy, where I break down different airplanes from their history to their engineering to how they fly. And occasionally I break down these aerodynamic principles as well. So if you enjoyed this video, feel free to give it a thumbs up, and also don't forget to subscribe to my channel, and I'll see you guys soon.